Every diagram you've ever seen of the universe is lying to you, not simplifying, not approximating. Lying. The number beneath that glowing sphere is wrong by a factor of more than 3, and the sphere represents a fraction of reality so small that calling it the universe is like calling your kitchen the country. The diagram says 13.8 billion light years. The actual radius of the observable universe is 46.5 billion light years. That discrepancy is not rounding. It is the entire story of how space expands, and why the universe you are shown is not the universe that exists. Right now, as you sit here, the oldest photons reaching your position have been in transit for 13.78 billion years. They covered 13.78 billion light-years of space, but the object that emitted them is not 13.78 billion light-years away. It is 46.5 billion light-years away. It moved. The universe carried it. The light travelled one distance. The source is somewhere else entirely. And the observable region, that 46.5 billion light-year bubble, is itself a sample, a window, a fraction of a total universe so much larger that no analogy survives the comparison. One cell in a continent. The diagram showed you the cell. It labelled it everything. If evenings like this are what you come here for, a subscribe helps this channel reach more people who need exactly this kind of quiet science. Now, let us begin. You have seen the diagram your whole life, a bright central point, planets in their rings, the solar system giving way to the Milky Way's spiral arms. Pull back, and the galaxy becomes one speck in the local group. Pull back further, and the local group sits in the Virgo supercluster, which is one thread in the vast cosmic web. The animation reaches its outermost edge. A label appears, the observable universe. A soft glow around a bounded sphere. The music swells. The narrator says something about vastness. And then the screen cuts away, and you're left holding the image. This is a picture of everything. It is not. The diagram shows you the observable universe. A specific, measured, physically precise region of space from which light has had time to reach us since the Big Bang. Not the universe. Not all of space. The portion of space whose photons have completed their transit to this position in the time available. The label observable is accurate technically. The problem is that it reads like a disclaimer nobody checks. Every eye in every classroom slides past it to the noun, universe. And universe sounds like everything. A surface is a property of an object. A horizon is a property of the observer. The horizon you see from a beach is not the edge of the ocean. It is the limit of your sight line from that elevation. Climb a lighthouse and the horizon retreats, not because the ocean changed, but because your vantage did. The ocean was always out there. You just could not see it from the sand. The edge in the diagram is a horizon, not a surface, not a wall. The limit of what light has had time to carry to you from a universe that began 13.8 billion years ago. Outside that horizon is not nothing. It is more universe, more space, more matter, more whatever the universe contains, whose light has not yet arrived, or in a significant portion of cases will never arrive at all. Now, the number that needs to be corrected. 13.2 billion light-years. You have heard this as the size of the observable universe. It appears in textbooks, in documentary narration, in science journalism, and it is wrong. Not approximately off. Wrong by a factor of more than 3. The radius of the observable universe is 46.5 billion light-years. The diameter, edge to edge, passing through our position, is 93 billion light-years. The 13.8 billion figure is a measurement of time, the age of the universe. If space were static, not expanding, then the farthest light with enough travel time would originate from 13.8 billion light-years away. clean arithmetic. But space is not static. Space has been expanding since the first fraction of a second after the Big Bang, and that expansion means the source of any ancient light has been carried away from us during the entire time the light was in transit. The oldest photons in your sky left their source when that source was roughly 42 million light-years from your position. They set off in our direction. The universe expanded while they travelled. The source kept receding. By the time those photons arrived, the expansion had carried the source to a current distance of 46.5 billion light-years. The photons travelled 13.78 billion light-years. The origin is now 46.5 billion light-years away. Both numbers are true. They measure different things. This distinction, light travel distance versus co-moving distance, is the difference between the universe as seen and the universe as it is. Cosmologists use co-moving distance when they describe where things are now. When you hear 46.5 billion light-years, that is where the source is today. When you hear 13.8 billion light-years, that is how far the photons travelled. The diagram was showing you a horizon. The universe does not end there. What lies beyond the horizon is not empty space waiting to be revealed. It is space that already exists, already full of whatever the universe contains in those regions, whose light has not arrived, or cannot arrive, from here. And the total volume of that space dwarfs the observable region by factors that defeat any analogy we have. The smaller problem is that the map is incomplete. The larger problem is what the boundary actually is, and why no instrument ever built, and no instrument ever conceivable, will move it past a certain point. Let us stay with what the diagram actually shows you, and what it withholds. The glowing sphere has a radius. 46.5 billion light-years in every direction from our position. That radius bounds a volume. The volume of a sphere with that radius in cubic light-years is a number with approximately 83 digits. 2 trillion galaxies sit inside it, the current best estimate from deep field surveys extrapolated across the full sky. 2 trillion. A 2 followed by 12 zeros. Each galaxy containing on average a few hundred billion stars. Each star, in principle, hosts to its own system of orbiting bodies, its own chemistry, its own history across billions of years. This is already past the point where the human mind can process quantities as quantities rather than as sounds. 2 trillion. You hear the words. You cannot feel the number. No one can. We are not built for it. Now look at the label again. Observable. This is the observable part. The full universe. By the most conservative estimate we can derive from the geometry of the observable region, is at least 250 times larger in volume. That is the lower bound. The number that requires the fewest assumptions, the mildest extrapolation, the most cautious reading of the flatness measurement from the Planck satellite. 250 times larger in volume, which corresponds to a linear diameter roughly 6 times larger than the observable sphere's diameter. If the observable universe is the diameter of a basketball, the minimum size full universe has a diameter of about 6 basketballs. But the minimum size estimate is not the expected result. The expected result under the physics of inflation, the period of exponential expansion in the universe's first moments, is a universe so much larger than the minimum that calling it 250 times larger understates it the way calling the distance from Earth to the Moon, a long walk, understates the walk. Inflationary models predict a full universe at least 10 to the power of 23 times larger in radius than the observable region. Write that out. 10 followed by 23 zeros, times larger. The observable universe is 1 part in 10 to the 23rd of the full universe's radius. If the observable universe were the size of a single atom, 1/10 billionth of a meter, the full universe would be approximately the size of the observable universe itself. The ratio eats its own comparisons. This is why the minimum size estimate is described as conservative, because the physics says the actual number is almost certainly incomprehensibly larger than 250. And 250 already defeats the human mind. The map showed you one cell. The continent it sits in is not 10 cells wide or 100. It is a continent in the most literal sense, a scale of territory so much larger than the cell that the cell cannot serve as a reference point for understanding the continent. Here is what the diagram never showed you, printed in small text beneath the glowing sphere. We have seen 1% of what is there, or less, depending on which estimate of total volume you use. The diagram is not wrong. The observable universe is 93 billion light-years across, 2 trillion galaxies. The numbers are accurate. The problem is what those numbers mean when you understand them correctly. When you hear observable, not as a synonym for visible or known, but as a precise physical qualifier meaning the region from which photons have reached us. When you hear observable, hear also, and the rest of it is not in this picture. Your brain accepted the diagram as complete because brains are built to accept visible boundaries as real edges. This is not a failure of intelligence. It is the result of 300,000 years of evolution, spent navigating a world where visible edges were real edges, coastlines, mountain ranges, the horizon at the edge of the savannah. The brain learned that what it cannot see can be treated as not immediately relevant. The organism that wasted cognitive resources on what it could not perceive did not outcompete the one that focused on what it could. In cosmological context, that same architecture produces a systematic and pervasive mistake. The image of the observable universe is filed as the universe, the way an image of the visible ocean from a beach is filed as the ocean. Both are true images of a portion of something larger. The ocean has a far shore. The universe, as best we can determine, does not. None of this was obvious until very recently. Edwin Hubble confirmed in 1929 that galaxies beyond the Milky Way exist and are receding from us. The cosmic microwave background was discovered in 1965. The flatness of the universe, which implies the observable region is a small sample of a much larger whole, was not measured precisely until the WMAP and Planck satellites operated from 2001 to 2013. The picture described tonight did not exist in its current form 50 years ago. We are living at the moment when the full extent of the problem has become visible to science. The diagram on the wall of every classroom in the world is a picture drawn before we understood how incomplete it was. The label is accurate. The impression it creates is not. There is a specific thought experiment that makes the light travel distance versus co-moving distance distinction visceral rather than abstract. You're watching a star explode. The supernova is brilliant, visible to the naked eye, one of the brightest events in the sky this year. The astronomers announce its distance. 1 billion light years. That number is the light travel distance, the distance those photons actually covered to reach you. But the star that produced them is not 1 billion light years away. It is further. The expansion of the universe has been carrying it away from us for the entire 1 billion years those photons were in transit. The star's current location, where it is right now in whatever form it exists after the explosion, is approximately 1.1 billion light-years away in co-moving distance. The difference is modest at 1 billion light-years because the expansion rate over that period is not enormous. Scale that up to the edge of the observable universe. The light travel distance to the CMB is 13.78 billion light-years. The co-moving distance, where the matter that emitted that light is now, is 46.5 billion light-years. The difference is not modest. the universe expanded by a factor of more than 100 between the moment of CMB emission and now, carrying the source from 42 million light-years away to 46.5 billion light-years away. The photons spent 13.78 billion years travelling across space that was simultaneously expanding beneath them, and they arrived not from where they started but from a transit whose starting point no longer exists at its original distance. The diagram shows you where things appear to be, not where they are. This is why the phrase "the observable universe is 13.8 billion light-years across" is not just imprecise. It is describing a different measurement from the one that matters for understanding the size of the observable region. What matters for understanding how much space we can see is co-moving distance, where things are now, and that number is 46.5 billion light-years for the radius, 93 billion for the diameter. The observable sphere is 93 billion light-years across. That is the universe you actually have access to, the region whose light has arrived, the space whose history is recorded in the photons currently reaching every telescope, every naked eye, every surface on Earth that the night sky touches, and it is a cell in a continent. Now think about what cell in a continent means for the question that started tonight. How big is the universe? The universe that you can see is 93 billion light-years across. The universe that exists is, at conservative estimate, at least 6 times wider in linear dimension, more than 250 times larger in volume. At the expected estimate from inflation, the ratio has no human-scale representation. When the narrator in a documentary says the universe is vast beyond comprehension, they are speaking about the observable region. They are speaking about the cell. What is actually vast beyond comprehension is the continent that contains it, and most documentaries do not have a shot for that. The animation cannot zoom out far enough, the background music cannot expand to fill the space. The narration says vast and moves on, and the brain hears this is the whole thing. It is not the whole thing. It was never the whole thing. And the label observable universe, which was always there, always precise, was always trying to tell you so. The evolution trap is worth naming precisely, because it is doing a specific thing to every person who encounters the diagram. Human spatial reasoning evolved in a world where all meaningful boundaries were real edges. The coastline ends at the water, the cliff ends at the drop, the forest ends at the clearing. In every environment human beings occupied for the 300,000 years before the invention of science, the visible boundary corresponded to a real edge of something. The horizon was not the boundary of the universe, but it was the boundary of useful information. What lay beyond the horizon, over the hill past the next valley, mattered for survival, and the brain was built to be curious about it. But what lay beyond the ocean's horizon, on the far side of a 3,000-mile expanse of water that no one in the group had any means of crossing, was so far from practical relevance that the cognitive architecture did not develop a strong default toward "and what is out there." The diagram exploits this architecture perfectly. It presents a bounded object. The brain files it as complete. What lies beyond the boundary is not represented, so the brain fills the absence with the assumption of nothing, not empty space, but the simple absence of anything requiring attention. The diagram becomes a map of reality. The edge of the diagram becomes the edge of reality. The label observable universe is processed as universe, because the qualifier slides past without engaging. The corrective is not to feel bad about this. It is to understand what is happening and replace the filing with a better one. The observable universe is not a complete object. It is a horizon. The horizon is not the edge of what exists. It is the limit of what light has had time to carry to this position in the time available. Everything the diagram shows is real. Everything outside the diagram is also real. The diagram is accurate. The diagram is incomplete. The universe you are shown is a sample, a large, real, accurately described sample. A sample, nonetheless. In 1964, 2 radio astronomers at Bell Labs in Holmdel, New Jersey, were trying to eliminate a noise source from a large horn-shaped antenna. The antenna had been built for satellite communications. The satellites it was built for were no longer in use. Arno Penzias and Robert Wilson had been given access to it for scientific measurements, and they had a problem. A persistent signal contaminated everything they tried to measure. It came from every direction equally. It did not vary with the time of day. It did not change with the season. It showed no correlation with any known astronomical source. It was uniform across the entire sky, in a way that made no physical sense if it originated from any conventional source, because conventional sources are located in specific directions, and this was coming from everywhere with identical intensity. They checked every component of the system. They found pigeons nesting inside the horn and removed them, along with what Wilson later diplomatically described as a white dielectric material. The signal remained, exactly as strong, exactly as uniform, coming from everywhere. They were trying to subtract the universe from their data. What Penzias and Wilson had found was the cosmic microwave background, photons that had been in transit for 13.78 billion years, cooling as the universe expanded, until they had lost enough energy to correspond to a temperature of 2.725 degrees above absolute zero. Cold enough to be invisible to human eyes, cold enough to be indistinguishable from equipment noise to any instrument not specifically designed to detect them, but real, present everywhere in the sky, arriving from every direction with the uniformity that only something truly filling the cosmos can produce. Penzias and Wilson received the Nobel Prize in Physics in 1978. What they had found marks the observable boundary, not the edge of space, the edge of what is visible. In the first 380,000 years after the Big Bang, the universe was a plasma, a dense, hot state of matter in which protons and electrons existed separately, interacting constantly with photons. In a plasma, photons are absorbed and re-emitted almost immediately after each emission. Light cannot travel. The universe was opaque in the most complete sense, not opaque the way smoke is opaque, where light can penetrate a little way before being absorbed. Opaque the way a star's interior is opaque, where a photon travels micrometers before being absorbed and re-emitted in a random direction, making no net progress outward for millions of years. The universe was a fog that light could not cross. As the universe expanded, it cooled. The relationship between expansion and temperature is precise. Double the volume, lower the temperature. After 380,000 years, the temperature fell below approximately 3,000 degrees Kelvin, the specific threshold at which electrons and protons can combine and stay combined, forming neutral hydrogen atoms. When that happened, the photons trapped in the plasma were suddenly free. The fog cleared. Light streamed outward in every direction for the first time. Those photons are the cosmic microwave background. They have been travelling for 13.78 billion years. The universe's expansion stretched their wavelengths from infrared to microwave. Their effective temperature cooled from 3000 Kelvin to 2.725 Kelvin, but they are still here, arriving every second, passing through your body right now, trillions of them per second, undetectable to your senses, carrying information about the moment the universe first became transparent. The CMB is the oldest light that can exist. Not just the oldest detected, the oldest physically possible. Before 380,000 years, the universe was opaque. No photon emitted before that moment survived to travel any distance. The CMB is a wall, but not in space. A wall in time. The earliest moment from which light could have departed and subsequently arrived anywhere. The Planck satellite, operated by the European Space Agency from 2009 to 2013, mapped this radiation across the full sky with extraordinary precision. The CMB is not perfectly uniform. It has temperature variations of 1 part in 100,000, tiny hot and cold spots distributed across the sky in a specific statistical pattern. These fluctuations are not random noise. They are the imprint of density variations in the early plasma at the moment of recombination. In the slightly denser regions, gravity was slightly stronger. After recombination, matter in those regions fell inward faster. Over hundreds of millions of years, the density grew until nuclear fusion ignited. The first stars turned on. Continued accretion produced the first galaxies. Galaxy clusters formed. The filaments and voids of the cosmic web assembled. Every galaxy in the observable universe, every one of the 2 trillion, grew from a density ripple that appears in the Planck data as a temperature variation of less than 1 degree in 100,000. The CMB is not merely a boundary marker. It is the record of the initial conditions of everything that followed. To read it correctly is to read the recipe for the universe we live in, and it is centered on you. Wherever in the universe you stand, the CMB surrounds you as a sphere, showing you the plasma as it existed 380,000 years after the Big Bang from your observation point. An observer in a galaxy 10 billion light-years from here has their own CMB sphere centered on their position, different photons, same physics. Every point in the universe is at the center of its own observable region. There is no universal center, no privileged position. The universe is, at its largest scales, the same everywhere from everywhere. This is the cosmological principle. It has been tested by the CMB's uniformity, by galaxy surveys spanning billions of light-years, by deep observations at every wavelength. It is one of the most thoroughly confirmed ideas in physical science. The CMB tells us where the observable boundary sits, and the flatness of the CMB's fluctuation pattern tells us something critical about what lies beyond it. Planck found that the geometry of space is flat, not curved inward, not curved outward, flat to better than 1% precision. This is significant not as an aesthetic fact but as a geometric constraint. A universe that curves back on itself, like the surface of a sphere but in 4 dimensions, would leave repeating patterns in the CMB. Looking in different directions, you would eventually be looking at the same regions of space from different angles. Temperature patterns would repeat across the sky in a systematic way, like tiles in a repeating floor. Planck found no such repeating patterns. This places a minimum size on the full universe, large enough that any curvature-induced repetition falls below detectable scale. The lower bound is a full universe at least 23 trillion light-years across, roughly 250 times larger in volume than the observable region. That is the conservative reading. The flat geometry is also consistent with an infinite universe, in which the full extent is not merely 250 times larger, but has no bound at all. What lies past the CMB is not nothing. It is the rest of the universe, extending in every direction, governed by the same physics, containing the same ingredients, structured by the same forces. The boundary is a horizon, not a wall. The universe continues past it exactly as the ocean continues past the beach horizon. The horizon is a limit of what light has had time to carry, not a limit of what exists. We found the edge by finding the oldest light. The light is everywhere. The edge surrounds us on all sides, and the universe it marks the limit of is far, far smaller than the universe that actually exists. The CMB contains more information than its uniformity alone. The specific pattern of temperature fluctuations encodes the entire physics of the early plasma in a way that cosmologists can read like a set of diagnostic readouts. The fluctuations have a characteristic angular scale, a preferred size at which temperature variations are most pronounced. This scale is determined by the distance sound waves travelled in the plasma before recombination. Before the fog cleared, the plasma supported acoustic waves, pressure waves propagating through the dense mixture of photons and matter, analogous to sound in air but moving at roughly half the speed of light. These waves created alternating regions of compression and rarefaction, hot and cold, oscillating in size. At the moment of recombination, whatever scale of compression was at its peak became a permanent imprint in the CMB. That scale, called the sound horizon, is approximately 150 megaparsecs in comoving distance, or about 490 million light-years. This scale appears as a characteristic angular size in the CMB fluctuation pattern and as a characteristic scale in the three-dimensional distribution of galaxies, the baryon acoustic oscillation peak. Both measurements confirm each other. Both confirm the geometry of the universe, because the apparent size of a known physical scale depends on the curvature of the space through which the light has travelled. Flat geometry gives one apparent size, curved geometry gives another. The measured angular scale matches flat geometry to better than 1%. Flat geometry with no repeating CMB patterns requires a full universe at minimum 23 trillion light-years across. That is the flaw. The measurement says, at least this large. The flaw happens to be approximately 250 times larger in volume than the observable region. But the flaw is not where the physics points. The physics of inflation, the mechanism that produced the flatness in the first place, operates on scales far larger than the flaw. Inflation did not stop at the minimum size consistent with Planck's measurements. It expanded space by factors that make the flaw look like a starting line. The true size of the full universe, in inflationary models that match the observations, is a number whose magnitude is largely a matter of which model you choose, all of which produce a full universe incomparably larger than the observable region. The CMB told us about the edge of the visible. The edge of the visible told us about inflation. Inflation told us about the continent, all from a noise signal two engineers were trying to eliminate. Let us stay with the Planck satellite for a moment, because its measurements are the foundation of everything quantitative said tonight about the full universe's size. Planck was launched in May 2009 and operated until October 2013. It surveyed the full sky in 9 microwave frequency bands from 30 to 857 gigahertz. It mapped the CMB temperature to a precision of better than 1 microkelvin, 1/1,000,000th of a degree. It measured the polarization of the CMB, which encodes additional information about the early universe and the processes that produced the fluctuations. The data release in 2013 and the subsequent release in 2015 set the current standard for cosmological parameter measurements. What Planck found, in the temperature fluctuations it mapped, was a power spectrum, a description of how much fluctuation power exists at each angular scale. The shape of this power spectrum is sensitive to the geometry of space, the density of matter and dark energy, the expansion rate, the duration and intensity of inflation, and the properties of the early plasma. Fitting the observed power spectrum to cosmological models allows those parameters to be measured simultaneously. The geometry measurement is the most direct. A flat universe gives one angular scale to the first acoustic peak, the characteristic bump in the power spectrum corresponding to the sound horizon. A positively curved universe gives a larger angular scale. A negatively curved universe gives a smaller scale. Planck measured the angle subtended by the first acoustic peak and found it consistent with flat geometry to within 0.4%. 0.4% deviation from flat as the error bar on the measurement. The universe's geometry is flat to that precision. Flat means infinite, or at minimum vastly larger than the observable region. The floor on the full universe's size, 23 trillion light-years across, comes from calculating how large the universe would have to be before any curvature produced a detectable deviation from flat in Planck's measurements. The universe is at least large enough that any curvature-induced repetition falls below the measurement's sensitivity. That floor is already 250 times the volume of the observable region, and it is a floor. The same Planck data that establishes the flatness also constrains the parameters of inflation, specifically the spectral index of the primordial power spectrum, which describes how the amplitude of quantum fluctuations varied with scale during inflation. Planck measured this index to be 0.961, consistent with simple inflationary models. A perfectly flat primordial spectrum would give an index of exactly 1.0. The measured index of 0.9635 means the amplitude decreased slightly at smaller scales, a prediction of most inflationary models, and a confirmation that inflation or something very like it happened. Inflation happened, the flatness confirms it, the spectral index confirms it, the horizon uniformity confirms it, and inflation produced a universe far larger than the floor the Planck measurement establishes. The diagram's number was 13.18 billion. The actual radius is 46.5 billion. And the full universe is a continent. All of this written in the microwave glow of the oldest light that can exist. The speed of light is 300,000 kilometers per second. Nothing with mass can reach it. Information cannot travel faster. This has been confirmed in every experiment designed to test it across 120 years of precision physics. It is not a technological barrier. It is a feature of the structure of space-time. The universe does not permit causally connected signals to propagate faster than light through space. Remove that comfort now, because what follows is not a violation of that rule, it is something outside the rule entirely. The expansion of space is not motion through space. Those are different categories. A spacecraft moving through space is subject to the speed of light limit. A photon travelling from a galaxy to a detector on Earth is subject to the speed of light limit. But when space itself expands, when additional space comes into existence between 2 points that are not gravitationally bound, nothing is moving through space. The space is growing, and the rate at which space can grow is not governed by the speed of light. General relativity places no speed limit on the expansion of space itself. The standard analogy, dots drawn on the surface of a balloon. Inflate the balloon, the dots separate. But the dots are not sliding across the rubber toward each other's edges. The rubber is stretching. The dots are stationary relative to the rubber immediately around them. Their recession from each other is expansion of the medium, not motion through it. Edwin Hubble measured the systematic recession of galaxies in 1929 and found that recession velocity is proportional to distance. The Hubble constant, the rate of expansion per unit of distance, currently sits at approximately 67 to 73 kilometers per second per megaparsec, meaning for every 3.26 million light-years of distance, recession velocity increases by 67 to 73 kilometers per second. At close distances, this is negligible. Andromeda is close enough that gravity overcomes the expansion, and it is approaching, not receding. But at large enough distances, the accumulation becomes absolute. At approximately 14 billion light-years, the Hubble radius recession velocity equals the speed of light. Beyond the Hubble radius, space between any point and us expands faster than light travels. A photon emitted from beyond the Hubble radius, aimed directly at our position, moves toward us at 300,000 kilometers per second through its local space. But the space between that photon and us expands faster than 300,000 kilometers per second. The photon loses ground. Under static conditions, it would never arrive. The Hubble radius is not fixed. In the early universe, the expansion rate was very high and the Hubble radius was very small. As the universe aged and the energy density decreased, the expansion rate slowed and the Hubble radius grew. Photons emitted in the early universe from beyond the Hubble radius could reach us if the Hubble radius expanded past them before they were too far away to recover. This is why the observable universe extends to 46.5 billion light-years, despite the universe being only 13.8 billion years old. The early expansion gave photons a difficult start, but the slowing expansion eventually allowed them to complete their transit. The observable boundary, 46.5 billion light-years, marks the outer limit of photons that just barely made it. Any photon from a source farther than that, under the conditions of the early universe, did not make it, and never will. Now there is a second, tighter boundary, the event horizon, currently at approximately 16.5 billion light-years. The event horizon is not the boundary of what we can see today. That is the particle horizon at 46.5 billion light-years. The event horizon is the boundary of what we can ever receive new signals from, given the present and future state of the expansion. This distinction matters because dark energy is causing the expansion to accelerate. Dark energy was discovered in 1998. Two independent teams, the High-Z Supernova Search Team and the Supernova Cosmology Project, were measuring the brightness of distant supernova to determine whether the expansion was slowing, as gravity requires. They found it was speeding up. The Nobel Prize in Physics in 2011 was awarded for this discovery. What dark energy fundamentally is remains unknown. What it does is specific. It acts as a pressure built into space itself, constant per unit volume, growing in total influence as space grows. As space expands and matter dilutes, dark energy becomes increasingly dominant. Its effect is to accelerate the expansion continuously, without limit, without end. A signal emitted right now from just beyond the event horizon will never reach us. Not because the physics blocks it absolutely, but because the accelerating expansion ensures the space between source and signal grows faster than the signal can close it, and that relationship will not reverse. The event horizon is the boundary beyond which this is currently true. What lies between the event horizon at 16.5 billion light-years and the particle horizon at 46.5 billion light-years? Galaxies we can currently see, 30 billion light-years worth of observable universe, containing ancient light that has already arrived, whose sources are now permanently beyond our reach for any new communication. We see them as they were. We cannot interact with them as they are. The ancient light continues to come, stretched and reddened as the sources recede, fading over billions of years toward undetectability. But no new information passes in either direction. The relationship is already over in every physical sense. We are seeing the memory of a connection that has already ended. Think about what that means precisely. Right now, looking at a galaxy 20 billion light-years away, you're seeing that galaxy as it existed roughly 8 or 9 billion years ago. You're receiving light from a time before Earth formed. The galaxy exists right now, in the sense that space continues, matter continues, whatever is happening there is happening. But whatever that is cannot reach you, cannot reach your instruments, cannot reach anything in your observable region. The event horizon is not a wall between us and something else. It is the point at which the universe's geometry has already made the decision for us. The horizon cannot be crossed, not technologically, not with patience, not in principle. It is not a limit of engineering. It is the behavior of space itself, accelerating away from the center of every observer, in every direction, faster than any signal can follow. And every second, as the expansion accelerates, more galaxies cross that threshold. The two groups of galaxies in the observable sky are worth sitting with. The first group sits within approximately 16.5 billion light-years. These galaxies are observable and in principle reachable by new information. A signal sent today will arrive someday, distorted and delayed by billions of years, but arriving. The round-trip communication time to a galaxy at 15 billion light-years is 30 billion years. The sun will have burned out, Earth will be gone, but the physics permits the signal to complete the crossing. The second group sits between 16.5 and 46.5 billion light-years. These galaxies are observable. Their ancient light has already arrived, but completely and permanently unreachable by any signal generated today. We see them. We can analyze their light, measure their redshift, estimate their mass and composition. We can build detailed profiles of what they were. We cannot tell them we exist. We cannot receive anything they send today or in the future. The connection is one-directional, and it is already over at its source. No ship reaches the second group, not at light speed, not at 99% of light speed, not because the crossing would take too long for any human life or human civilization to sustain, though it would. Because even a photon moving at the maximum possible speed through space cannot close the gap faster than the gap grows. You could not reach those galaxies if you were a beam of light. You could not reach them if you were information itself. The horizon is not a wall you run into. It is the absence of a there to reach. There is a version of this that is even harder to absorb than the abstract physics. Pick a specific galaxy, a real one. The Pinwheel Galaxy, Messier 101, a spiral galaxy in the constellation Ursa Major, roughly 21 million light-years from Earth, currently inside our observable region by a comfortable margin, well within the event horizon. Its light reaches us with no trouble. We have mapped it in multiple wavelengths. We know its mass, its size, its rate of star formation, its composition. The Pinwheel Galaxy is currently receding from us at approximately 1,500 kilometers per second due to the expansion of space. That recession velocity will increase over time as the expansion accelerates. In approximately 150 billion years, the Pinwheel Galaxy will have crossed our event horizon. From that moment, any signal it emits will never reach us. Its ancient light, all the light it has emitted up to the crossing moment, will continue arriving for an enormously long time after that, stretched and reddened, fading over billions of years, but any light emitted after the crossing moment will fail to complete the crossing. 21 million light years, a galaxy we can examine in extraordinary detail right now, a galaxy that will become permanently unreachable within 150 billion years. Now pick a galaxy at 40 billion light-years, already beyond the event horizon, already in the group whose current signals will never reach us. We can see it. The ancient light from when it was closer has already arrived and is sitting in our telescope data. But whatever is happening in that galaxy right now in 2026 cannot be detected from Earth. Not with better instruments, not with more sensitive receivers, not with any technology operating within the laws of physics. The event horizon is not a wall the technology runs into. It is the boundary at which the physics has already decided, and the event horizon is at 16.5 billion light-years. The observable universe extends to 46.5 billion light-years. That means more than half the observable universe. By volume, the large majority of it is already in the second group, observable by ancient light, already permanently out of reach. You're looking at a sky in which most of the content is already gone in every practical sense. The ancient light is still coming. The relationship is already over. The universe you can interact with is a small inner sphere. The universe you can observe is a much larger outer sphere. Between those two spheres is a vast region of observable but unreachable space, growing smaller as the event horizon contracts. The diagram never showed any of this. It showed you one number, called it the universe, and cut away. There is one more way to sit with this that brings the abstraction into something more felt. Right now, without knowing it, you're on the boundary of the two-group division. The light reaching your eyes from the most distant observable galaxies is ancient light. Some of it has been travelling since before the sun existed. Some of it left its source before Earth had formed, before the solar system condensed from interstellar gas, before the molecular cloud that produced the sun had even begun to collapse. That light set off toward us when its source was a young galaxy in an earlier phase of the universe, and it arrives now at a position where the source is 40 or 45 billion light-years away, and completely beyond any reciprocal interaction. You're receiving one-directional light from a universe that has already moved on. The light in your sky is not a picture of the present. It is a collection of pictures from different pasts, each photon arriving from a different moment in history, the most distant ones from the most ancient moments. The sky is not a view across space. It is a view across time, compressed into a single instant of observation. And most of the objects in that view have already crossed the event horizon. Their ancient light is still arriving. Nothing we send today will reach them. What they send today will not reach us. We're exchanging light from the past in a universe that has already moved the participants out of reach. The diagram did not show you any of this. It showed you a bounded sphere labelled universe. The sphere is a sample. The view inside the sphere is a view across time, not space. Most of the 2 trillion objects in the view are already gone in the only sense that matters for interaction, and the diagram called it everything. 93 billion light-years, diameter, edge to edge, passing through our position. 2 trillion galaxies, hundreds of billions of stars in each. This is already past the point where numbers function as quantities rather than sounds. You hear 2 trillion, and your mind does what it does with numbers too large to feel. It files them as a lot and continues. It is a bubble, a finite sphere, a sample. And the region outside it is not a modest extension. The key to estimating the full universe's size is inflation. The period of exponential expansion in the universe's first fraction of a second. Understanding what inflation was is understanding why the full universe is so much larger than what we can see. Alan Guth proposed cosmic inflation in 1980 to solve 3 specific problems that the standard Big Bang model could not explain without it. The first problem: the universe is almost perfectly flat. The matter and energy density is very close to the critical density separating eternal expansion from eventual recollapse. Any deviation from the critical density in the early universe amplifies over time. For the geometry to be as flat as observed, the early universe would have had to be fine-tuned to 1 part in 10 to the 60th power. That is 10 followed by 60 zeros. No physical mechanism in the standard Big Bang model explains that tuning. Inflation explains it. The enormous expansion smooths any initial curvature the way inflating a balloon. Enough makes any small patch of its surface look flat. The second problem: the cosmic microwave background is uniform to 1 part in 100,000 across regions of the sky that, without inflation, could never have been in causal contact. Regions separated by more than a few degrees of angular distance in the sky are separated by distances too large for light to have travelled between them before the CMB was emitted. Their uniformity requires either extraordinary fine-tuning of initial conditions or a mechanism that placed them in causal contact before inflation separated them. Inflation provides that mechanism. The entire region that became our observable universe was, before inflation, small enough to reach thermal equilibrium. The third problem: grand unified theories predict the existence of magnetic monopoles, isolated north or south magnetic poles without their counterpart, produced in the early universe in large quantities. None have ever been detected. Inflation dilutes any monopoles produced before its onset to densities so low that detection becomes effectively impossible. Inflation solves all three by the same mechanism: an enormous, rapid expansion of space driven by a quantum field in the first moments of the universe. The expansion factor in most inflationary models is at least 10 to the power of 26. A region smaller than a proton expands to a size far larger than the current observable universe, in a time so short that writing the number of seconds requires 36 negative digits after the decimal point. Here is what that expansion implies for the full universe. Inflation did not expand only the region that would become our observable bubble. It expanded everything. The space surrounding what would become our observable region was expanded by the same enormous factor. The total volume of space produced by inflation is, in nearly all inflationary models, incomparably larger than the observable portion. Our observable universe grew from a tiny connected subregion of the inflated total. The rest, the unobservable extension, is the vast majority of what was created. The Planck satellite measured the geometry of the observable universe at better than 1% precision, flat. A flat universe with no repeating patterns in the CMB requires a full universe at minimum 23 trillion light-years across, 250 times larger in volume than the observable region. This is the conservative lower bound. The number derived from Planck's flatness measurement assuming the smallest universe consistent with no observable repetition. If the full universe has the scale predicted by most inflationary models, the radius of the full universe is at least 10 to the 23rd power times larger than the radius of the observable universe. 10 followed by 23 zeros. Let us try to make that ratio human for a moment. If the observable universe, 93 billion light-years across, 2 trillion galaxies, were the size of a single red blood cell, about 8 micrometers in diameter, then the full universe at the lower bound estimate would be roughly the size of the continental United States. 5 million meters across, the red blood cell against the continent, everything you have ever seen, every photon that has ever reached a human instrument, every galaxy named, catalogued, analysed, argued about, every telescope ever pointed at any patch of sky. The sum total of all human cosmological knowledge inside a single cell on the surface of a continent. At the more aggressive inflationary estimates, the continent becomes a galaxy, then becomes a number of galaxies that the analogy cannot sustain. 1 year before Guth proposed inflation, nobody had this picture. The observable universe was understood to be large. The full universe was assumed to be roughly the same kind of large, maybe infinite, but without the specific quantitative arguments that inflation provides for why and by how much. Inflation gave the full universe a mechanism and a scale. The scale is not comfortable to sit with. You were taught the observable universe is vast beyond comprehension. That is true. It is also a 15 millionth of the volume of the most conservative estimate of the full universe. The vastness you were told about is the cell. Nobody told you about the continent. If tonight is landing the way we hoped, a like or subscribe helps this channel reach more people who need exactly this kind of quiet evening. Now, is the continent identical to the cell, or does it differ in ways that change what it means to exist out there? There is one more layer to the inflation picture that matters for tonight. In many inflationary models, those motivated by quantum field theory and string theory, inflation does not end everywhere at once. The quantum field driving inflation fluctuates. In most of the volume, inflation continues indefinitely. In small regions where the field fluctuates to its minimum energy state, inflation ends and a hot early universe forms. A bubble of normal physics embedded in a still inflating background. Our observable universe is one such bubble. Other bubbles form in other locations. The total inflating volume grows without limit, continuously producing new regions with ended inflation. This scenario, called eternal inflation, produces a structure in which the question, how large is the full universe, has no fixed answer. The total volume is not merely incomprehensibly large, but is growing without bound, adding new regions of ended inflation at a rate faster than any volume measurement can keep up with. The fraction of the total occupied by any specific bubble, including ours, trends towards zero over time, regardless of how large that bubble is. Our observable universe, in this picture, is not a small fraction of a large universe. It is a fraction so small that no number exists to represent it in a total that has no upper bound. This is what the word observable was always quietly implying. And now you have seen what was on the other side of it. The minimum size estimate deserves more than a number. Let us walk it. 23 trillion light-years across, at minimum. Take the observable universe, 93 billion light-year across 2 trillion galaxies, and multiply by 250 in volume. The observable universe is the sand grain in the basketball analogy. Except the basketball is not the full universe. The basketball is the minimum estimate. At the full inflationary prediction, the basketball becomes a grain of sand inside another sphere, and that sphere becomes a grain of sand inside another sphere, and the regression continues until the numbers become meaningless. At the minimum size estimate, 250 times the volume, 250 times 2 trillion galaxies at the same average density, 500 trillion galaxies in the minimum estimate of the full universe, 500 trillion, a 5 followed by 14 zeros. If every star in the Milky Way were a galaxy, you would still need 10 million Milky Ways to hold 500 trillion galaxies. That is the flaw, the estimate that requires the fewest assumptions, the most conservative reading of the least aggressive inflationary model consistent with Planck's measurements. Most physicists who work in this area expect the true number to be incomparably larger. The Planck satellite did not design inflation. It measured a universe whose properties are consistent with having emerged from inflation. The flatness it found, geometry indistinguishable from perfectly flat, is exactly what inflation predicts. The scale and pattern of CMB fluctuations match inflationary predictions. The absence of monopoles matches inflationary predictions. The horizon uniformity matches inflationary predictions. Every test that can be applied to the question, did inflation happen, returns the same answer, consistent with yes. And if inflation happened, the full universe is vastly larger than the floor, not by a factor of 2, not by a factor of 1,000, by a factor that requires exponents of exponents to write, and even then the writing does not convey the meaning. The cell in the diagram, the continent it sits in. The continent does not end at the edge of the drawing. Imagine a point 1 trillion light-years from here. The temperature is 2.725 Kelvin. The cosmic microwave background arrives from every direction. Local matter, galaxies, their stars, their chemical histories, is distributed at roughly the same density as locally. The large-scale structure of filaments and voids extends in every direction. An observer at that point with our instruments would see what appears to be an ordinary sky. Ordinary in the precise sense, organized by the same physics, at the same statistical density, with the same characteristic scales. Looking toward Earth, if they could, which they cannot, they would see nothing. We are in their dark. They are in ours. What fills that dark is answered by the cosmological principle. The cosmological principle states that the universe is homogeneous, the same composition and density everywhere, averaged over large enough scales, and isotropic, presenting the same statistical properties in every direction from every point. These are not assumptions made to simplify calculations. They are conclusions derived from observation. The CMB is uniform to 1 part in 100,000 across the full sky. No preferred direction, no warm hemisphere, no cold axis. Uniform in every direction that Planck's instruments could resolve, which was every direction to finer than 1/10 of a degree. That uniformity, if the CMB came from a universe that differed significantly from region to region, would be impossible to achieve. It tells us that the region that became our observable universe was, before inflation expanded it, uniform enough for that uniformity to be preserved. Galaxy surveys confirm the same picture at lower redshifts. The Sloan Digital Sky Survey mapped hundreds of millions of galaxies across nearly a quarter of the sky, and confirmed that matter is distributed uniformly on scales larger than a few 100 million light-years. The 2-micron Sky Survey confirmed isotropy in the infrared across the full celestial sphere. The Dark Energy Spectroscopic Instrument, operating since 2021, is extending this picture with higher precision and to greater distances. Every comprehensive survey at every wavelength confirms the same conclusion. On the larger scales, the universe is the same everywhere. These observations are made within our observable bubble. They cannot sample what lies beyond our horizon directly. But the cosmological principle holds throughout the observable region, with no gradient, no preferred direction, no hint that the physics changes as you approach our boundary. There is no physical mechanism that would cause the laws of physics to change at precisely the boundary of our observable region, which would require our position to be cosmically special in a way the cosmological principle itself contradicts. The most defensible conclusion, 1 trillion light-years from here, the universe contains the same ratio of dark matter to ordinary matter to dark energy, the same nuclear physics, the same atomic structure, the same electromagnetic forces, the same gravitational constant, the same tendency for matter to clump under gravity into galaxies, stars, and whatever surrounds them. What that means concretely, galaxies exist there, in roughly the same density per cubic megaparsec as locally. Those galaxies contain stars. Stars evolve through the same nuclear burning sequences and die in the same variety of ways. Some fraction host planetary systems. Some fraction of those planetary systems include rocky planets in the temperature range where liquid water can exist. Whether chemistry on any of those planets has produced anything we would recognize as interesting is a question the cosmological principle cannot answer. What it answers is, the raw material is there, and the laws governing it are identical. Now the thought experiment that captures what this actually means. A civilization located 2 trillion light-years from Earth has its own observable universe centered on their position. Our Milky Way is billions of light-years outside their observable boundary. No photon from any human instrument has reached them. No signal we have transmitted or could transmit will ever reach them. The expansion ensures the separation is permanent, not temporary, not a delay to be overcome with patience or technology. The structure of space-time built the separation into place before any civilization existed. That civilization, if it exists, might build instruments and study its own CMB, survey its own galaxy distribution, measure the Hubble flow in its own observable region, identify the same dark energy, measure the same matter density, find the same flat geometry, build the same cosmological picture that we have built. ask the same question we're asking tonight. Is there more than we can see? And arrive, using the same physics and the same logic, at the same answer. Yes, enormously more, extending by factors that defeat description. Two civilizations, same physics, same cosmological model, same picture of a universe vastly larger than either can observe, permanently unable to know about each other, not hidden, not blocked, simply on opposite sides of a horizon that the geometry of expanding space-time created before the first stars ignited. The universe beyond our horizon is not a void. It is the other 99.999% of the universe, and it looks, on the larger scales, like this. There is one subtlety worth adding. Statistical similarity does not mean identical. The quantum fluctuations that became the seeds of cosmic structure were different in different regions. The specific galaxies that formed, their sizes, their merger histories, their stellar populations, these vary. Two regions with the same average density produce different specific arrangements. The unobservable universe is not a copy of the observable universe. It is a different realization of the same statistical distribution. Every region unique in its history, every region governed by identical laws. What those unique histories contain, whether any of them have produced anything we would call notable in the ways that interest us, cannot be known from here. The tools are the same everywhere. What they build is not identical. Consider the symmetry of that situation for a moment. Whatever we feel when we contemplate the vast, unreachable extension of the universe, the silence, the distance, the permanent separation, any civilization in any other observable bubble looking outward at its own horizon experiences the same. The physics guarantees it. The expansion that created our bubble created their bubble. The horizon that bounds our view bounds theirs. The isolation we experience as observers in one bubble is the universal condition of all observers in all bubbles. Every point in the cosmos is equally central and equally isolated. This is not a consolation. It is a precise description of the structure of the universe. The emptiness between our observable region and every other observable region is not empty in the sense of containing nothing. It contains the universe. It contains more galaxies than we can count. It contains more stars, more planetary systems, more chemistry, more time. The word empty belongs to the space between planets or between stars. What lies beyond our horizon is not absence. It is presence on a scale that no language we have successfully represents. The diagram called it nothing. It always was everything. There is a way to make this more concrete and a way to leave it abstract. Both are honest. The abstract version, the cosmological principle confirmed by observation throughout the observable region, implies the same physics everywhere. The unobservable universe contains what the observable universe contains statistically: galaxies, stars, the periodic table of elements, the fundamental forces, time, the concrete version. In the time it took the light from the CMB to travel from its source to your position, 13.78 billion years. Every galaxy in the observable universe evolved from its earlier star-forming phase to whatever it is now. Andromeda went from a proto-galactic cloud of hydrogen to the 1 trillion star spiral it is today. The Milky Way assembled its bar, its disk, its halo. The local group settled into its current configuration. In the unobservable region, the same 13.78 billion years elapsed. The same gas collapsed. The same stars ignited. The same stellar generations lived and died, seeding the interstellar medium with the heavier elements produced in their interiors. The same gravitational evolution played out. At the end of those 1378 billion years, in a region 1 trillion light-years from here, there are galaxies that have been running their chemistry for exactly as long as the galaxies we can see. Duration inversion. If the observable universe's 13.78 billion years of stellar chemistry was enough to produce, on at least one planet in at least one solar system, observers capable of reconstructing the history of the universe, then the unobservable region, running the same chemistry for the same duration, under the same laws, had the same opportunity, multiplied by the ratio of full universe volume to observable universe volume, multiplied by a factor of at minimum 250, and probably by a factor that has no name. Whatever the universe does in 13.78 billion years, it does it everywhere simultaneously. We're not seeing a process that happened here and not elsewhere. We're seeing one local instance of a process running in every part of the universe, with identical ingredients and identical rules, simultaneously with ours. The diagram showed you one local instance. It called that instance the universe. One last point about what the cosmological principle means for tonight's central question. We started tonight by saying the diagram lied. The lie was specific. The labelled region is not the universe. It is the observable universe. The continent beyond the cell exists, is real, and is full. But here is the thing the cosmological principle adds to that statement. The continent beyond the cell is not full of something alien, something different in kind from the cell. It is full of the same kind of thing, the same galaxies at the same average spacing, the same stars at the same average stellar populations, the same fundamental forces and constants, the same arc of cosmic history playing out under the same rules. The lie in the diagram was not, here is a picture of a small part pretending to be the whole. The lie was deeper. Here is a picture of something special pretending to be the universe. Because the diagram, by showing only the observable region, implicitly suggested that the observable region is the universe, the whole, the complete thing. It is not special. It is representative. It looks like the rest because the rest follows the same rules. The cell is a faithful sample of the continent, which means the 2 trillion galaxies in the diagram are not a collection unique to our particular bubble of observable space. They're a fair sample of what the continent contains. Multiply them by the ratio of full universe volume to observable universe volume, and you have an estimate, not a count, but an estimate of the galaxies in the full universe. At the minimum estimate, 500 trillion. At the inflationary estimate, a number written in digits that would fill more pages than exist. The universe beyond our horizon is not empty. It is not different. It is more of this, extended by a factor that even tonight, after all the time we have spent on it, still defeats the telling. The diagram showed you the sample. It called the sample everything. Now you know the population. The boundary is moving away from us. The event horizon, the line beyond which new signals cannot reach us, currently sits at 16.5 billion light years. Every year, the accelerating expansion pushes the accessible region slightly tighter. Galaxies that were within the boundary last year are now outside it. Their last signals are already in transit, heading toward us on a transit that will take billions of years to complete. After those signals arrive, nothing further from those galaxies will ever come. This is not a catastrophe that is approaching. It is a process that has been running since dark energy became dominant, roughly 5 billion years ago. The event horizon has been shrinking for 5 billion years. It will continue shrinking for the remainder of the universe's existence. Consider what dark energy means when carried to its logical conclusion across cosmological time. Dark energy does not dilute. As the universe expands, the density of ordinary matter drops. Spread the same mass across a larger volume and the density falls. Dark energy is a property of space itself. As space grows, the total amount of dark energy grows with it. Its density per unit volume remains constant. Matter becomes less dense. Dark energy does not. The ratio of dark energy to matter increases continuously, without limit, as the universe expands. Dark energy's influence on the expansion grows continuously, accelerating the expansion further, which creates more space, which contains more dark energy, which accelerates further. The process does not reach equilibrium. It compounds. In 150 billion years, 11 times the current age of the universe, the last galaxies outside the local group will have receded beyond any detection threshold. The local group is the Milky Way, Andromeda, the Magellanic Clouds, and a few dozen smaller companions. By that epoch, Andromeda and the Milky Way will have merged into a single large elliptical galaxy. The merger is already underway. The two galaxies are approaching each other at approximately 110 kilometers per second and will collide in roughly 4 to 5 billion years. What emerges from that collision will remain gravitationally bound to the other local group members. That merged remnant, surrounded by a few dozen companion galaxies, will be all that is visible in any sky from any position in the local group in 150 billion years. The rest, the 2 trillion galaxies currently visible from Earth, every cluster and supercluster and filament and void currently mapped by any survey, will be gone from the sky, not destroyed, not gone from physics, gone from any observable sky. The expansion will have carried them past detection thresholds so completely that no instrument of any conceivable design could find them. In the time it takes for the Sun to orbit the galaxy twice from now, approximately 450 million years, approximately the same number of years as separate us from the first fish walking on land, the CMB will have redshifted perceptibly from its current temperature. In 150 billion years, the CMB will have cooled from 2.725 Kelvin to approximately 0.01 Kelvin, 1,000th of a degree above absolute zero. The wavelengths of the photons will have stretched to hundreds of meters. Detecting them would require antenna structures of continental scale. Whether any technology could realistically operate at those wavelengths is genuinely unclear. The large-scale structure of the universe, the cosmic web of filaments and voids that current surveys map in such detail, which extends hundreds of millions of light-years and is one of the primary confirmations of the Big Bang cosmology, will leave no observable trace in the far future sky. The galaxies that make the filaments visible will have receded past detection. The record of large-scale structure that existing surveys are compiling right now is a record that can only be compiled during this era. Now consider a cosmologist born into that far future era. They inherit a sky containing a small collection of galaxies. They can study those galaxies with extraordinary precision. They can measure stellar compositions, internal dynamics, element abundances. They can detect whatever remains of the CMB at its red-shifted wavelengths, if their instruments are sensitive enough and large enough. From those observations, they attempt to reconstruct the history of the universe. The hydrogen and helium abundances created in the first 3 minutes of Big Bang nuclear synthesis are encoded in stellar compositions, but so are centuries of subsequent stellar nuclear synthesis. Disentangling primordial from produced abundances will require knowing the star formation history of the local group across hundreds of billions of years of activity. Without the global CMB as a calibration anchor, without the galaxy distribution showing the Hubble flow, without the supernova data that reveal dark energy, the pieces of evidence we have now that form a mutually confirming picture, the far future cosmologist faces an underdetermined problem. Multiple cosmological models may be consistent with the surviving evidence. They might reconstruct the correct picture. Brilliant and careful reasoning from limited evidence has succeeded before in science. They might not. They might look at a sky with a few dozen galaxies and conclude that the universe has always been a small, compact collection of gravitationally bound systems. They would be wrong. and without the dispersed evidence, they might have no way to determine that they are wrong. The knowledge that 2 trillion galaxies once filled the observable sky, knowledge we possess right now in this era, may be irrecoverable in the far future if the chain of understanding breaks at any point in the intervening hundreds of billions of years. This is not merely a loss of data, it is a loss of the capacity to know. The universe is structured such that the evidence for its own history is temporary. The window during which that evidence is accessible is not permanently open. It is open now. Every galaxy that crosses our event horizon today, and some do, continuously, silently, as the expansion carries more and more of the observable sky past the threshold, removes a piece of the universe from the domain of what can ever be known from this position. The removal is permanent. There is no recapture. There is no waiting long enough. The physics built the separation into place, and the physics does not reverse. The bubble is shrinking, the window is closing. Not in any human lifetime, not in any period relevant to civilization as it exists now. But the process is real, it is continuous, and it began 5 billion years ago when dark energy first became dominant. There's a philosophical pivot available here, taken exactly once because once is enough. The physical barriers described in this script, the horizon, the expansion, the acceleration, the shrinking event horizon, are all real and permanent. They are not temporary engineering problems awaiting better solutions. They are properties of the universe. But beneath those physical barriers lies something that is harder to sit with than impossibility. It is the fact that knowledge itself is time-limited, that the universe produces a window of cosmological accessibility, an era in which observers exist and evidence is present simultaneously, and that window is not permanent. The evidence disperses, the window closes. Future minds, however brilliant, inherit less. We are in the window, not because we deserve it, not because anything decided that this era should be the one in which the full picture is available. The physics of expansion and cooling and structure formation happened to produce, between the moment the universe became cool enough for complex chemistry and the moment the evidence disperses beyond recovery, an era in which creatures made of stardust can look up and reconstruct, in considerable detail, the history of everything. We happen to be those creatures. We happen to occupy that era. The window is open now. One more layer to the shrinking. Right now, in 2026, the event horizon sits at 16.5 billion light-years. Galaxies up to that distance can still exchange new signals with us. Galaxies beyond that distance cannot, but the light from galaxies beyond the event horizon is still arriving. We are still receiving the ancient light of galaxies that crossed the event horizon years ago, decades ago, millennia ago. The light they emitted before crossing is still in transit, still making its way toward us. How long does that light keep coming? For a galaxy that crossed the event horizon 1 billion years ago, at a distance of 17 billion light-years, its last light, emitted at the crossing moment, is currently about 16 billion light-years away, travelling toward us at the speed of light. It will arrive in approximately 16 billion years. The galaxy's light will not simply stop one day, it will taper. The light from longer and longer ago, increasingly redshifted, increasingly stretched, will continue to arrive for billions of years after the crossing, until the signal has redshifted to wavelengths beyond any conceivable detection. This means the sky is showing you a graveyard of relationships. The 2 trillion galaxies currently visible include many whose information pipeline is already closed. Their light is still coming. The connection is already over. The ratio gets worse over time. As the event horizon contracts, the fraction of the observable sky that has already crossed it increases. In 50 billion years, most of the currently observable galaxies will have crossed. Their ancient light will still be arriving, more redshifted and fainter, but new information from them has already stopped coming. The sky will look relatively full for a long time. It will feel deceptive because the light will still be there, and only careful measurement of increasing redshifts will reveal that the observable sky is showing you an increasingly old picture of an increasingly unreachable universe. In a billion years from now, a short time by cosmological standards, shorter than the gap between us and the dinosaurs by only a factor of 1,000, the sky will look almost identical to today's sky. The same galaxies, the same CMB, the same apparent distribution of large-scale structure, but the event horizon will have contracted by a measurable amount. More galaxies will have crossed it. More of the observable sky will be showing ancient light from permanently unreachable sources. The shrinking is not dramatic. It does not announce itself. It proceeds through a slow arithmetic that no single human life can perceive. But it is continuous. It began 5 billion years ago, and it will not reverse. The bubble is shrinking, not quickly, continuously. There is a historical comparison that makes the 150 billion year timescale feel less abstract. In 150 billion years from today, the large-scale evidence for the Big Bang cosmology will have dispersed beyond recovery. Let us work backward from that. What events in the past are separated from today by timescales that help anchor the number? 150 billion years. The current age of the universe is 13.8 billion years. So 150 billion years from now is 11 universe lifetimes from today. The universe has been running for 13.8 billion years. 11 more runs of the same length. In that time, the sun will have exhausted its hydrogen fuel, expanded to a red giant engulfing Earth, collapsed to a white dwarf, and cooled toward a black dwarf. That sequence takes roughly 10 billion years. After the sun's death, 140 billion years of additional time elapses before the last galaxies outside the local group recede below detection. In that 140 billion years, stars that have not yet formed will form and die. Stars forming right now in stellar nurseries across the Milky Way will spend billions of years on the main sequence, swell to giants, seed the interstellar medium with heavy elements, and fade. Their remnants will cool. New generations of stars will form from the enriched gas. The process will run many generations, and then, in the far future sky, the stars of the local group will slowly exhaust the available gas, and star formation will taper. The sky will grow quiet. And in that quiet sky, with no external galaxy visible, a cosmologist will look outward and see nothing beyond the local group's familiar companions. They will have inherited a universe that looks nothing like the one we occupy today. The knowledge we possess right now, the full cosmological picture, the evidence for 2 trillion galaxies, the confirmation of dark energy, the measurement of the CMB, the mapping of the large-scale structure, is a product of this specific moment. It was not available 50 years ago. It will not be available 150 billion years from now. It exists now, assembled from instruments that exist now, reading a universe that is still legible. The window does not stay open forever. It is open tonight. Why does the size of the unobservable universe matter to a person lying in a dark room? Practically, it does not. Nothing beyond the observable horizon changes the temperature of this room, the outcome of any decision you will make, or anything affecting the conditions of any life you could live. The expansion of space beyond 46.5 billion light-years has no influence on your circumstances. In the most direct accounting, the continent beyond your cell is irrelevant to everything practical. But the question is not asking about practicality. It is asking about orientation, about what it means to know what kind of universe you're actually in. The history of cosmological displacement has a pattern. Copernicus in 1543. Earth is not the centre of the solar system. Then, the solar system is not at the centre of the galaxy. Then, the galaxy has no special position in the universe. Then, the universe has no centre at all. Each displacement changed nothing practical. Each changed the frame of reference within which everything else is understood. The difference between thinking you are at the centre and knowing you are not is not a difference in circumstances. It is a difference in what kind of thing you are. Tonight adds one more layer, not a displacement within the observable universe. That displacement is already complete. A displacement of the observable universe itself, from the universe to a sample of the universe, from the thing labelled everything to one cell in a continent of more of the same. The diagram lied not just about the numbers, it lied about the category. The thing in the diagram was described as the whole. It is a part, a specific, bounded, physically defined part whose light has had time to reach our position, and whose extension beyond our position is so large that the diagram had no hope of representing it honestly, even if it had tried. Now sit with what is true simultaneously. The Planck satellite exists. Its CMB map is public data, downloadable by anyone, representing the most precise cosmological measurement in history. The Sloan Digital Sky Survey catalogued hundreds of millions of galaxies and confirmed the large-scale structure of the cosmic web. The Dark Energy Spectroscopic Instrument is extending that catalogue while you read these words. The supernova data that revealed dark energy was gathered between 1994 and 1998 by two teams working in parallel and in competition, and the Nobel Prize awarded for it in 2011 confirmed that the observation was real and the interpretation correct. LIGO has detected gravitational waves from merging black holes and neutron stars, opening an entirely new observational window on the universe that did not exist before 2015. Every piece of the picture assembled tonight is drawn from real measurements, real instruments, real data that has been independently confirmed by multiple methods operating on different physical principles. The case is not speculation. It is the most thoroughly tested cosmological model in the history of science, and all of it is available now, in this era, because the physics of the current moment in cosmic history makes it available. The CMB is warm enough to have been found accidentally in 1964 by engineers cleaning bird droppings from a communications antenna. Penzias and Wilson were not looking for it. It found them, because in this era the signal is that strong. In 1 trillion years, no antenna of any design will find it, because the signal will have cooled and stretched past any practical threshold. But right now, it fills every direction of the sky, arriving at full strength, carrying the full record of the universe at age 380,000 years. The galaxies are close enough to be catalogued by the billions, their redshifts measured, their distances computed, their distributions mapped into the three-dimensional picture of the cosmic web. In 150 billion years, most of them will be undetectable. Right now, they are everywhere in the sky, bright enough to fill deep field images with thousands of objects in a patch of sky the size of a grain of sand held at arm's length. The supernova data that revealed dark energy is available because Type Ia supernovae are bright enough to detect at cosmological distances with current technology, and enough of them are happening in enough observable galaxies that a survey of years can accumulate a statistically significant sample. The evidence for dark energy was waiting to be found by anyone who looked carefully enough at the right data. In the far future, when the galaxies hosting those supernovae have receded past detection, that evidence will not be findable. We're living in the era when the universe is maximally legible. Not perfectly understood. Dark energy's fundamental nature is unknown. The origin and mechanism of inflation are not directly confirmed. The nature of dark matter remains unsolved after decades of searching. But the broad picture, the observable region, the unobservable extension, the accelerating expansion, the shrinking event horizon, the cosmological principle, is built from confirmed observations and tested theory, not from speculation. Take a breath here. The picture that is now inside your head was not available to any human being 50 years ago. It was not available in 1970. The flatness of the universe was not measured precisely until the early 2000s. Dark energy was not known to exist until 1998. The full scale of the observable region was not accurately understood by most people until recent decades, and is still misrepresented in most classroom materials currently in use. You have been given, tonight, the most accurate picture of the universe available to any humans who have ever lived. Not the final picture. Science produces no final pictures, but the current one. The one incorporating the most data, the most precise instruments, the most thoroughly tested frameworks. The one that is more complete than any picture any generation before yours possessed. And that picture shows a universe whose observable portion, vast already beyond comprehension, is one cell in a continent of more of the same, bounded by a horizon that cannot be crossed, sitting inside a full universe so large that no number you have access to represents it honestly, governed everywhere by identical rules, accessible in this specific era, at this specific moment in cosmic history, because the physics happen to produce a window in which observers and evidence coincide. You are in the window. The diagram on the classroom wall showed you the cell. It labelled it everything. Now you know what was outside the frame. There is one more thing to say about what it means to know this, and it is the thing that is easiest to skip over because it sounds like a comfort when it is actually just a description. You have not changed the universe by learning its size tonight. The continent does not know you understand it now. The cell does not feel different because you know what it sits inside. The physics of the observable region and the physics of the unobservable region are identical and indifferent to what any observer understands about either one. What has changed is the frame. The diagram on the wall of every classroom shows you a bounded sphere and calls it the universe. You now know that sphere is a sample, a window, a region defined not by the edge of what exists but by the limit of what light has had time to carry to this position. The universe continues past every edge of that diagram with no diminishment of any kind. Same matter, same rules, same physics, same density of galaxies per unit volume, more stars than the observable region contains, more planetary systems, more time. And you know this because you are alive during the specific era of cosmic history in which the evidence for it is measurable. The CMB is warm enough to detect. The galaxies are close enough to survey. The dark energy is measurable in supernova redshifts. The Hubble flow is visible in millions of objects. The case is present, confirmed, accessible. This window, the window in which an observer in our universe can look up and reconstruct what the universe is and how large it is open now. It will close, on timescales that make civilization look temporary, which it is. The evidence will disperse, the window will close, the CMB will cool past detection, the galaxies will recede past detection, the supernova data will be locked inside civilizational archives that may or may not survive. The picture that is now inside your head was assembled from evidence that is available in this era and will not be available in every era. You received it tonight. You can hold it. You can carry it. You can hand it to someone else. The diagram lied. The label told the truth. The universe is far bigger than you think. Here is a thought experiment that closes the loop on what it means to know this. In 100 years, a modest span of human time, shorter than the gap between now and the moon landing, the Vera Rubin Observatory will have completed its decadal survey of the southern sky and produced a catalogue of 20 billion galaxies. DESI will have mapped 50 million galaxy redshifts in 3 dimensions. CMB experiments will have measured the polarization of the cosmic microwave background to higher precision than Planck achieved. Gravitational wave detectors sensitive enough to detect the primordial background from inflation may be operating. The picture that is currently described as the most accurate cosmological model ever assembled will have been refined further, the error bars narrowed, the uncertainties reduced. None of these refinements will change the structure of tonight's picture. The observable region will still be 46.5 billion light-years. The full universe will still be at minimum 250 times larger in volume. The event horizon will still be shrinking. The cosmological principle will still hold. The fundamental picture, cell in a continent, window open, diagram lying, will still be accurate. The refinements will be the kind of accuracy improvement that matters enormously to the scientist doing the measuring, and will produce precisely zero correction to what any of tonight's sections said. In 1 trillion years, a span of time that makes the current age of the universe look like a rounding error, none of this evidence will be available. The CMB will have cooled beyond detection. The galaxies will have receded beyond detection. The Hubble flow will be unmeasurable because there will be no detectable galaxies at the distances where the flow would be visible. Any civilization living in the far future will inherit a sky with a small collection of gravitationally bound companions and a darkness beyond them that gives no indication of 2 trillion galaxies. Between now and that future, a window. The window is wide open right now. The evidence is here. The picture is available. The diagram lied, but the measurement that corrects it is also here, also available, also sitting in public data archives accessible to anyone with the mathematical background to read them. You received the correction tonight. In words, not data. But the underlying thing, the universe as it actually is, vastly larger than any diagram, bounded by a horizon that cannot be crossed, sitting inside a full extent that defeats all description. That thing is real, and knowing it is available to anyone who spends an evening looking carefully at what the physics has to say. The window is open. You looked through it tonight. The next time you see a diagram of the universe, in a textbook, in a documentary, on the wall of a museum, look at the edge of that glowing sphere, the soft boundary where the image gives way to white space. That boundary is not the edge of the universe, it is a horizon. The limit of what photons have had time to carry to us from a universe that began 13.8 billion years ago. Beyond it, in every direction, the universe continues. The same matter, the same physics, the same laws, extended by a factor that defeats every analogy we attempted tonight. And we attempted several. The label at the edge of the diagram says, Observable Universe. It always did. The word observable was always there, quietly, precisely, doing enormous work that no one explained. What it was observing out of was a continent. What it was showing you was one cell. Every diagram you've ever seen of the universe was lying to you. That was where tonight started. The number beneath the sphere is wrong by a factor of more than 3. The sphere represents a fraction of reality so small that no comparison at human scale survives the ratio. The observable universe, 2 trillion galaxies, 93 billion light-years across, already past every frame of reference, is a bubble inside a vastly larger space that operates by identical rules and is permanently, structurally, geometrically inaccessible from this position. The space between us and the continent is not empty. It is the universe. It was always the universe. The diagram just never tried to show it. Thank you for staying all the way through this one. If tonight gave you something worth keeping, a like or subscribe helps more people find their way here. It means more than you might think. The universe is patient. The closing line of tonight needs one more beat. Not a summary, not a restatement, just what is true. The universe is patient. It has been expanding for 13.8 billion years. It will continue expanding for a time so long that no number taught in any school adequately represents it. The galaxies will recede, the CMB will cool, the evidence will disperse, the window will close. Right now, it is open. The evidence is here. The diagram lied. The universe is far bigger than you think, and you now know precisely how much bigger and exactly why.